Salutations YouTube, this is DRE, and today we're going to be going through problem 274 of LeetCode, H-index. Okay, the problem goes as so. Given an array of integers citations, where citations I is the number of citations a researcher received for their ith paper, return the researcher's H-index. Okay, so we're dealing with an array. And this is how I understand it. 7, 4, 9, 3, 2, right? Okay, so this right here is the ith paper. This is the first paper, or I guess in this case, 0th paper, because we're using 0 index arrays. This is the 0th paper, and the 0th paper has 7 citations. It has 7 citations. The first paper has 4 citations, and so on. That is the array we're dealing with. So now what about this H-index stuff? According to the definition of H-index on Wikipedia, the H-index is defined as the maximum value of H, such that the given researcher has published at least H papers that each have been cited at least H times. So the H-index satisfies this statement. At least H is going to be the maximum value that satisfies this statement, which is at least H papers with at least H citations. So let's pick a value for H. Let's say 3 citations. How many papers have at least 3 citations? We have 1, 2, 3, and 4. There are 4 papers with at least 3 citations. So this does validate. I mean, this does satisfy this statement, but is it the maximum value? Let's go ahead and test all the values in this case. So let's try 7. How many? Let's go ahead and move this down. I'm going to create a sort of chart, which on this side is going to be the number of citations, and on this side is going to be the pages, number of papers. So let's see, 7 citations. With 7 citations, how many papers are there? 1. There's only 1. For 4 citations, how many papers? No. For 9, no, whoa. For 9 citations, how many papers are there? There's 1 paper. For 7 citations, how many papers are there? There's only 2. For 4, there is 1, 2, and 3. For 3, there is 4, and for 2, there's 5. So we're looking for the maximum value, where the maximum value for, I guess, citations that has an equal to or greater amount of papers with that citation. So for here, right here, we have 4 citations, but only 3 papers. That is not going to satisfy this statement down here. But down here, we have 3 citations with 4 papers. So that is going to satisfy this statement in this case. So let's think of a couple of solutions. One solution, in this case, which I'd say is the most simple solution, is to go through this counting the number of papers. The number of papers that have a given number of citations. Let's start at 1. If we were to citations is going to be our, I guess, the number of papers we're counting for a given citation, and the number of papers on this side. So let's start at 0. Well, actually, no, let's start at 1. For 1, how many papers have at least 1 citation? 1, 2, 3, 4, 5. 5. So currently our maximum H value is going to be 1. Let's try 2. For 2, we have 5 still. So our maximum H value is now 2. Let's try 3. And our maximum H value is going to be 1, 2, 3, 4. This does satisfy this statement down here. So it is a valid, possibly be our H value. So 3 is our new max, and we keep going until we get to the very end. Once we get to 9, we'll get only 1, and so on. Of course, we probably won't get to 9. We'll probably only get to 5, as it won't make sense to count beyond 5, because there can't be, if you only have 5 papers, then the maximum H value you can have for those 5 papers is 5. If all those papers have 5 citations, then your H value will be 5. For 9, it is impossible for the H value for this given 5 papers will be 9, because there aren't 9 papers with 9, there aren't at least 9 papers with 9 citations. So we're going to count only to 5. For there's 1, 2, 3, and then 5, that's 1, 2. So we're only going to count to 5 in this case for this solution. Our second solution will be a little less, a little bit more complex, and it will require a little bit more thinking, but it will complete the solution. It will acquire the solution a lot quicker. The O complexity of this solution will be O of n squared. The reason being, for this, we're going to iterate n times on this side, and for each time we're going to search n indexes. So that's going to be n plus n plus n 5 times, which is going to be n times n. I mean, not 5 times, but n times. Okay, so another solution will have the search complexity of O of n log n. That will be the search complexity. That will be the time complexity for our next solution. Okay, for this solution, we're going to use 2 test cases. The reason we'll be using 2 test cases will become clear as I go through the solution. Okay, so for this solution, our first step is to sort the array. The reason for that will become clear once we sort the array. So if we sort this first array, what we'll get is 1, 2, 4, 4, 7, and 9. Next thing I'm going to do is graph this, so that I have a visual representation of what we're dealing with here. Okay, now that I have it graphed, let me go ahead and explain what we got going on here. So that's this. On the bottom we have I. We have indexes I on the bottom. And on the top we have number of citations. So this array is represented by this graph. This graph represents this array. Vice versa, doesn't really matter. Okay, so let's go ahead and start searching from the back. Let me start searching from the back. If we start searching from here, we'll see that there is one paper. I'm gonna write in this notation: paper, number of papers, 2, number of citations. So right here we have one paper with 9 citations. Let's move on next. We'll see that these 2 papers have at least 7 citations. Next, we have 3 papers with at least 4 citations. Then we have 4 papers with at least 4 citations. 5 papers with at least 2 citations. And 6 papers with at least 1 citation. Okay, now from here we can probably already see that our H value is going to be equal to 4, as our H value is going to be the maximum value that satisfies the statement H number of papers with at least H number of papers with at least H number of citations. And right here we have 4 papers and 4 citations. And that's how we get our our H value in this case. So how would we implement this kind of search using program? So how I would do it is this right here, this value right here is it correlates. So I'm gonna say number of pages correlates with whatever this value is. How do we get this value? This value is going to be, well, if we take the length of the array, 1, 2, 3, 4, 5, 6, right? Which is going to be the length of the array. I'm gonna call it n. The n is going to be the length of the array. And if this is the fifth index in the array, 0, 1, 2, 3, 4, 5, 9 is the fifth index in the array, then, and this is going to be that, n minus I in this case is going to give us 1. In this case is going to give us 2. So this correlates with the number of pages that we've counted so far. So if we're right here, if we're at this one, our index is 0, 1, 2, 2. 6 minus 2 is 4. We have counted 4 pages so far. So n minus I correlates with that. So we are waiting for when I'm going to say this list is going to be equal to h. Let's say it's equal to h. So h sub I, let's say h sub 0 in this case is going to be equal to 1. Going to be equal to 1 in this case. H sub, let's say 3, 0, 1, 2, 3 is going to be equal to 4. So from there, we're looking for when the number of pages is greater than or equal to the number of citations at a given index. So we're waiting for when n minus I is greater than or equal to h of I. And that will give us a value that satisfies this statement. And if we search from the back, because it's in ascending order, or because of the way we're traversing it, it's descending as we go further into the as we iterate further into the array. After we encounter the first time that this happens, when we encounter that the number of pages exceeds the number of citations, there is not going to be another h value that is greater than this. So for example, once we're right here, we see that the number of pages is equal to 4 and the number of citations is equal to 4. Once we go here, right here, the number of pages is equal to 5 and the number of citations is equal to 2. After this, the number of citations will continue going down. Our h value will continue going, our possible h values will continue going down. So our maximum h value will be the first one that we encounter that satisfies this condition right here. However, there are some cases that we will miss if we use this solution alone. So that's why I included this this case right here. So let's go ahead and address that one. All right, first things first, we're going to want to sort this array. All right, but the array is already sorted, so there's really nothing to do right here. So if we go ahead and represent this array right here, we'll get this. So let's go ahead and do our search from the back using this rule right here to find the h value. So right here, we have encountered 1 page with 4 citations. Right here we have 2 pages with 4 citations, and right here we have 3 pages with 1 citation. So this is the first case in which the number of pages exceeds the number of citations. So our h value is equal to 1, right? That is, however, that is, although our algorithm seems well thought out, this is incorrect. Our h value in this case is going to be equal to 2. Why is it 2? because of something that we overlooked earlier. When we encounter one page, for example, if we're this little robot in a room and we're receiving these pages, with these citations, and this is us. This is our little robot or big robot. Here's my big robot, and it receives a page. If it receives a page, what it should note down is we have, if we're receiving it in reverse order, then we know that pages are only going to get smaller. I mean, the number of citations are only going to get smaller from here. They're either going to stay the same or get smaller from here. So right now, this one has, let's say this one has 7 citations, but only 1 page. So right now, at this moment in time, we have currently counted 1 page, right? And the number of citations for this page is 7. So our possible H index so far, if we stopped right now, our H index is going to be 1, because the number of citations we have is going a value that satisfies H pages with H citations. So far, a possible value is going to be 1. We have 1 page, and so far we have 7 citations, which is at least 1. So that value, that satisfies our statement here. Let's say we receive another paper, right? And this one has 5. This one has 5 citations. So far we've encountered 2 papers, and each of them have at least 5 citations. In other words, we can also say that we have 2 pages and each one of them has at least 2 citations. So in this case, we'll be using 2 as our H value after we encounter 2 of these papers. If we encounter another paper, right, and we get another 5, then we've encountered 3 pages, and our citation count for we have 3 pages with at least 5 citations. So in other words, we have 3 pages with at least 3 citations, and that is going to be our H value. So what we can take from here is the H value also correlates with the number of pages we encounter, given that the number of citations we encounter so far is greater than the number of pages. So if, for example, if the number of pages we encounter so far isn't greater than or equal to the citation value at this given moment, what we should do is add another case for when this is if this, otherwise, if this is not true, then we've encountered a page that has more citations than the number of pages we've counted so far. Well, then our value, our citation value, our H value is going to then be, I'm going to say max H value is then going to be equal to n minus I. It will be equal to the number of pages that we encounter so far. But the moment we encounter this right here, then we know we're not going to encounter any higher H value, any possible higher H value from there. So let's try this. 4, we encounter 4. and we only have one page so far. So we have one page and our value is 4. So our maximum right now is going to just be equal to the number of pages that we've encountered so far, which is 1. Let's say we encounter 4 again. 4 is still, the number of pages we have so far, which is 2, is still not greater than or equal to the number of citations we have right now, which is 4. So we'll set max equal to 2 now. I'll write down the value of max here. Max is 1, max is 2 here. And let's say we encountered 3. Once we encounter 3, we've encountered 3 pages, and that's greater than or equal to the number of citations we have so far, which is 3. 3 is greater than or equal to 3. So we're going to then set max equal to 3. And after this, we don't need to count anymore. So after this, we'll break. We'll stop searching. But let's say hypothetically, let's say we received a 1. If we received a 1 right here, then the number of pages that we encountered so far is 3. And that 3 is greater than 1. But does that mean that we should set max to 1? That is incorrect, because if we set it to 1, we will make the same mistake we made down here. We should then just take whichever one is greater. Max is then going to be equal to the maximum of either our current max or our current citation value, which in this case, our current max right now is 2, and our citation value is going to be equal to 1. So it will take 2 instead of 1 in this case. So this leaves our maximum value as 2, and we're done searching. We find our H value using this. So let's go ahead and implement this using Java. All right, so I've already established some kind of test environment. So these citations are then put into this test case, and our test cases are going to be executed, are going to be passed to our hindex method, which will find the hindex of the given arrays. I already have some test cases and the expected values for each test case. So let's go ahead and program our solution. So first things first, we need to sort the array. So we'll go ahead and sort citations. And in order to do that, we have to import java.util.arrays. Then from there, we're going to set n, which I'm going to name length because I like descriptive names. I'm going to set it equal to the length of the array. And I'm also going to have a max, which is going to be 0 at the beginning. This doesn't really matter what the value, well, actually it does matter. It does matter that it's going to be equal to 0 because that's going to be the minimum possible of citations. So from here, we're going to go ahead and implement our loop. We'll say index, since we're searching from the back, is going to be equal to length minus 1, which is going to put us at the last possible, last searchable index of the array. And while this index is greater than or equal to 0, which will allow us to search all the way to the beginning of the array, index minus minus. Okay, so our first case, which is going to be if length minus index, which is the number of pages, is greater than the number of citations at this given index, then what we need to do is set max equal to the maximum between our last max and our citations, our current citation. current number of citations. Otherwise, what we're going to do is set max equal to length minus index, which is going to be, we're going to set max equal to the number of pages we have so far. And after that, we return max. So let's go ahead and run this solution and see if we get the correct answers. 34102, 34102. All right, now that's pretty convincing, but let's go ahead and run that against LeetCode to see if we get the correct solutions. All right, that's pretty spectacular. I'm gonna be honest, this memory fluctuates quite a bit, so if you submit it like twice, the memory will jump back down to 40 megabytes or something like that. I've gotten as low as 40.4 in the past. I'm not sure. But yeah, that is this entire video. I hope I helped explain this problem well to you. Leave a comment if I explained anything off or if I missed anything. I am learning. So I do appreciate that if you would do that. Otherwise, have a wonderful day. Adios.